Hi, welcome to IB Biology. This is the very first chapter, A1.1, and it's all about water. Pretty easy chapter. It should go by really fast. If you're in a rush, watch this video on ×2 speed. It will still be very understandable, and you can get through this video much faster. There will be HL and SL parts. I will tell you what part is HL only, so you don't have to worry about that, SLs. Let's start. These are the main takeaways from this video, from the chapter itself. If you can do all of these by the end of the video, you should be fine and ready to go. Water is a medium of life, right? We cannot live without water. We drink water every day. Water is all around us. It's crucial. So what is water? Since middle school, we know that water is H2O, right? 2 hydrogen atoms and 1 oxygen atom. But how does it really look? This is one molecule of water. See, it kind of looks like Mickey Mouse. The big atom is oxygen, while the 2 small ears are hydrogen. The hydrogens have a partial positive charge, while the oxygen has a partial negative charge. But since the oxygen is bigger, the negative charge is slightly more powerful. So the side with oxygen is usually pulls atoms slightly towards it. Electrons, sorry. Also, one thing to know is that the bond between the oxygen and the hydrogens are covalent bonds. Chemistry students, you guys should know what that is. But for biology, if you only take bio, you don't really need to know what it is. Just know that between oxygen and hydrogen, it's covalent bonds. However, between different molecules of water, you have hydrogen bonds. So between the hydrogen of one molecule to the oxygen of another molecule, it is hydrogen bonds. So this is how they bond, as you can see in these photos. So one important thing that you should know and the IB wants you to know, because a question might come in paper 2, is how to draw a water molecule. Well, not really just one, but they want you to kind of connect them together. And I'm going to show you how to do that and to make sure you get all points if that question comes. Okay, it's really, really simple. So first, you just get your oxygen, and then you get your 2 hydrogens. As I mentioned before, these are covalent bonds between them. If you want, you can add the charge. So it's kind of like a 6, but you can kind of do it like a 6. I don't think they really care. And then oxygen has the negative, and the hydrogens have the positives. Now you draw another water molecule and connect them. So you get a dotted line that represents hydrogen bonds, and you draw an oxygen, and then a clear line, a line with no dots, like a solid line, is what represents a covalent bond. So you draw the 2 H's coming from the oxygen. Usually the IB wants you to draw 3 different water molecules, so let's do that here. And from the hydrogen, we get another hydrogen bond to an oxygen, and the oxygen is connected using covalent bonds to 2 hydrogens. There it is. That's how you draw water molecules. Moving on, there are two terms that you need to know involving water, and that is cohesion and adhesion. They're similar, but not really. So cohesion is the attraction between molecules of the same substance. So the hydrogen bonds that make water molecules stick together. So those bonds between each single molecule of water. And like examples of this in real life is how water moves up the xylem. So basically, imagine it like water molecules holding hands. One gets pulled up, the other gets pulled as well because they're holding hands with the one that already got pulled up. So and then it's like kind of a chain. They're all holding hands. If one gets pulled, they all get pulled. So that's basically what cohesion is. And also, fun fact, it's what allows some insects to walk on water. Not magic, but just cohesion. They're because the surface tension and they're light because of surface tension and the insect themselves are light. They're not able to break those hydrogen bonds that holds the water together. So they're able to kind of like bounce on water. What is adhesion? Adhesion is the attraction between molecules of different substances. So unlike cohesion, they're not the ones that are holding together. It's the ones that it's when water, for example, holds on to a cup, or for example, in real life, it would be when water holds on to the xylem, the walls of the xylem. Okay, so water as transport in animals. That's something that we should know. So metabolism, you've heard the word. Basically, we're not getting into details, but let's just talk about the small things in the body. For example, cytoplasm is a complex mixture of dissolved substances in the blood. And guess what? What's the solvent? Water. Everything is dissolved in water in the cytoplasm. Dissolved enzymes catalyze specific chemical reactions, which is metabolism. So, again, water is crucial for metabolism for simple reactions in the body. So, it's also used for transport, of course. So, substances are transported as an aqueous solution in both plants and animals. Plants have two systems, which are the mineral ions that are transported in the xylem sap, and products of photosynthesis are transported in the phloem sap. But that we'll get into details in the other chapters, so don't really worry about that much. Just know that in animals and plants, they both use water as transport systems. So yeah, as I said, in animals, we transport many ions like Na and Cl, which comes from salt, amino acids, glucose, fats, and etc. So there are four physical properties of water that you should know about: buoyancy, viscosity, thermal conductivity, and specific heat. We're gonna look into each one right now. So okay, firstly, buoyancy. When an object is immersed in a fluid, the fluid exerts an upward force on the object. This force is equal to the weight of the fluid displaced by the object. If the density of the object is lower than the density of the fluid, the force acting on the object due to buoyancy will be greater than the force due to the gravity, and the object will float. That's very wordy, but it's important that you understand it. I'm gonna help break it down for you. Basically, it's the force that allows an object to float. For example, in water, a floaty is not as dense as water because there's air inside, and air is less dense than water. So this allows a floaty to float on water, and that force that pushes it up is what buoyancy is. So in living tissues, bone is denser than water, while lung tissue and adipose tissues are both less dense than water. However, living organisms have an overall density close to water, which kind of makes it easy for us to use, well, not us specifically, but animals to use water as a habitat because they do not need that much energy to float. When you go swimming, you obviously feel yourself floating if you completely lie down. Don't you just kind of float all the way up if you don't panic? That's because of buoyancy, that force pushing us upwards. Bony fish have an air-filled swim bladder which they use to control their overall density. So this swim bladder in the picture can grow or shrink depending on how they want to how deep they want to go. Um, and it kind of allows them to either float or sink. So air is much less dense than living organisms, which is why organisms have to generate lift to stay airborne. So, for example, birds, they need to kind of push themselves down to be able to fly. And that's because they're way denser than air. Secondly, we've got viscosity. So, viscosity is basically just the stickiness of the fluid and how easily it flows. So an example of low viscosity is propane, and high viscosity is treacle. Basically, viscosity is the internal friction of a liquid. I'll give you an example. Fluid flows through a tube. Velocity is greater in the center than in the edges, so there is internal friction. The more viscous a fluid, the greater the friction and the resistance to flow. So the thicker it is, for example, honey, if you kind of get a cup of honey and you pour it on your desk, the honey is going to drip slowly. That's because there's more friction on the cup and and it's kind of way thicker. But if you get a cup of water and you dump it on your desk, it will just fall out of the cup and kind of go everywhere, right? Because it flows much easier than honey. So water is less viscous than honey. Something that increases viscosity is solutes. So if water is dissolved with salt, it's gonna become somewhat thicker than pure water. Next, thermal conductivity. Basically, it's the rate heat passes through a material. So water has a relatively high thermal conductivity. Fats and oils conduct about 25% as quickly as water, and air around 5% of that. So aquatic warm-blooded animals are at much greater risk of the loss of body heat than land-based warm animals because water will be able to conduct their body heat much more than, for example, us humans. While we're in the air, since air isn't as good as a thermal conductor, we don't lose as much heat from our body as if a seal, for example, or us when we're in water. That's why we're much colder in the water than we are in the air. Okay, so how does this really benefit us humans? Well, since blood contains a lot of water, it allows heat to be carried from parts where it is generated to where it's needed. Specific heat is the heat required to raise the temperature of 1 gram of a material by 1 Celsius or Kelvin. The specific heat capacity of water is 4.18. That's a number that you should generally know. For air, the value is only 1.01. So you see how much higher the specific heat of water is to air. Water has a relatively high specific heat capacity because of those hydrogen bonds that we talked about. They restrict molecular motion, which create that surface tension, which allows some insects to walk on water. It's important that you kind of connect these dots. For the temperature of water to increase, hydrogen bonds must be broken, and energy is needed to do this. So, hydrogen bonds are pretty strong, so more energy is required to break them. To cool down, water must lose an equally large amount of energy. Obviously, right? If you have this amount of energy to break these bonds, you need to take out the same amount of energy to cool them down, to bring them back together. The temperature of water remains relatively stable compared to air because of this. So it's much harder to heat water and cool water, which kind of balances it out. While in air, it's like 4 times less. It's 4 times easier to do that. which means aquatic habitats are more thermally stable than terrestrial habitats. So very easy thing to know. You just need to know the difference between air and water generally. Easy questions in multiple choice. So just basically, air is less dense, it's less viscous, lower thermal conductivity, and lower specific heat capacity. So yeah, as easy as air is less or lower than water in basically all four properties. Okay, so there are like two animal case studies that you need to know. They're not that hard. They're quick, easy. There's the ringed seal and the black-throated loon. There has been a few questions in past papers about these, so they might come up. Water is more viscous, so the seal uses more energy to move through it. It has a streamlined body shape that allows it to kind of move through it more easily. It also has a blubber of fat under its skin, which helps it maintain its body temperature, since water has a high thermal conductivity. The black-throated loon flies, so air is less dense and provides far less buoyant force, so it must expend more energy to stay aloft than the ringed seal has to stay floating in water. Water has greater thermal conductivity than air, as we've mentioned, so it conducts heat away from the bodies of submerged animals, while air acts as an insulator. Okay, so this next part is for only HL. SL, you are completely done with this unit. If you know everything, you can move on. HL, there's such a small but really easy part left, and honestly, it's kind of fun. It's astrobiology, a bit of history and space, and it's not really much into bio, but it's pretty fun to learn about. Have you ever thought of the question, where did water on Earth come from? Well, there are nearly 1.4 billion cubic meters of water on Earth, and 98.3% is in liquid state. So how on Earth, pun intended, did all that water come to begin with, right? It is unlikely that water was on Earth when it was formed, because it was way too hot for that, and since water has a boiling point of 100 Celsius, it would have all boiled away. There are so many hypotheses for the origin of water, but one of the most supported ones, and the one that you should know about in the IB, is that it is delivered to the Earth by colliding asteroids. Currently, the big asteroids rarely ever hit Earth, but there is evidence of much heavier bombardment during the first few 100 million years after Earth's formation. So it was this big hot rock, and big asteroids kept on hitting it, and those asteroids contained water. So the more and more asteroids hit, the more and more water came to Earth and stayed there. So it is likely that asteroids that collided with Earth early in its history contained more water than the asteroids that hit now. Okay, so how was water retained on Earth? So all these asteroids hit and hit, but what kept them on Earth? Why didn't the water just float away or leave or evaporate? Well, the distance of the Earth, you should know these two important points. The distance between Earth and the Sun makes sure that sunlight never raises the temperatures too high enough for the water to boil, or too low for it to completely freeze. So liquid water is retained much more easily than vapor because of the cohesion, as we said, from hydrogen bonding. So they hold on to each other. Earth also has a relatively strong gravity compared to other planets. So that's kind of what keeps water in place. It holds the oceans tightly to its surface, holding gases within the atmosphere. So that's also a really crucial point. That's why water doesn't just float away, it's because of gravity. There is evidence of the presence of water on Mars. It's just like a little extra fun fact, but it's thought that most of this water was used in hydration reactions with minerals. But on Earth, the quantities of these minerals were less, so the water was not all used up. So, Goldilocks, what is she doing in bio? Well, I don't know if you know the story, but Goldilocks goes into three bears, a house that has three bears, a mom, a dad, and a baby. Well, she tries to eat their porridge, and one is too hot, one is too cold, but one is just right. Well, this metaphor is used for the habitable zone around any star, not necessarily our sun, but any star has a habitable zone, and this is called the Goldilocks zone because it's not too hot, not too cold, but just right. Liquid water is essential, as we've said this whole time. So if a planet is too close to the star, water will vaporize. Too far away, and the water will freeze. So in the Goldilocks zone, the temperatures allows water to exist in a liquid state, which is crucial for life, or at least what we think is crucial for life. The location of the Goldilocks zone depends on the size of the star and the amount of energy it emits. You should know that. You should, if a simple question might come where they ask, what does the location of the Goldilocks zone depend on? And you could just say the size of the star and the amount of energy it emits. It also depends on the size of the planet, which determines the strength of gravity and the atmospheric pressure. Okay, so these are the main takeaways from this chapter from the beginning of the video. I hope now you guys can completely do all of these. If not, and you're in a rush, I'd say just move on, and hopefully you can come back to it during using past papers if you have time for that as well. But yeah, just move on. The other chapters are definitely more important, and a lot of this is just common sense. I'm sure you'll be fine. If you have any questions, comment them. You can email me, but I'd rather you comment them so other students can, if they have the same question, they can immediately get the answer. And yeah, so help out the others. Any questions, do not hesitate. I'll answer as fast as I can, and I'll see you guys next time. Thank you. Bye. Good luck.